Okay, everyone, let's get started. Sorry, I'm running late. So I'll try to make this quick so we can get started on the next lab. We have our midterm exam on Thursday, March 5th in class closed book, and the topics will be everything we covered so far in class. Last week we had quiz 2 and quiz 3 due, I believe. So I'll go over those really quick. I'm going to fly through these fast, so if you have any questions, though, stop me. What percentage of an SPI channel's master to slave bandwidth can be utilized when performing a series of single write transactions? It's 100% because with SPI you can achieve 100% of the bandwidth on exchanges, not on transactions, but at the lower level protocol where you're doing exchanges, you can basically hold, the SS. You can assert the SS and you can continuously stream data. Does that make sense? Now you might say, like, what opposed to what? Well, opposed to like UART, where you have a start bit and a parity bit and a stop bit, which effectively steal bandwidth from the data, right? Whereas with SPI, you don't have bandwidth stealing for the control signals. In a daisy chain SPI connection between master and end slaves, how many clock cycles are required to complete a full exchange? A daisy chain is when you have you connect the slaves serially. And in this case, if you have one slave, which is kind of the case that we covered, that we focused on in the class mostly, there was 8 cycles, right, to do an exchange. With 2 slaves, it would be 16. So with n slaves, it would be 8 times n cycles. What is C-pool and C-fa for the exchange below? I mentioned the way that, well, C-pool is easy. You just look for whatever clock starts out at. So C-pool is high. C-fa is a little bit harder. But the way that I always look at this is if the data gets a head start on the clock, then C-fa is 1. In this case, it did not get a head start because the clock and the data were changing at the same time. So C-fa is 1. What data is written in the transaction below? Unfortunately, this is tricky. You have to just kind of count. You have to just count cycles and do a manual serial to parallel conversion. So in this case, the first 8 cycles is the header. The second 8 cycles is the data. And if you look at the data line, actually, we're looking at which one, MOSI or MISO? MOSI, we're asking what is written. What data is written in the transaction? So this is a transaction, not an exchange. I mean, well, there's 2 exchanges, 1 transaction. Remember, the transaction protocol is built on top of the exchange sequence. And so when you say what data is written, you're going to be looking at MOSI because we're writing from the master to the slave, and MOSI is master out slave in. And the data is 111000101. Okay? Bus protocol requires 3 wires named D in, D out, and clock. Is this a synchronous or asynchronous? Well, this would be synchronous because there's a clock in there. Unless someone just had a signal called clock that wasn't actually a clock, but I don't know why they would do that. What bit is missing in the timing diagram below? This is a UART with 5 data bits, least significant bit first, odd parity, 1 stop bit. So the parity is odd. There's only 1 missing bit, so the question must be talking about transmit side. The first bit is the start, that's not counted. Last bit is stop, that's not counted, and there's 1 stop bit. So we're looking at the number of 1 bits starting from the second bit and ending with the next to last bit, right? So that would be a 0. Actually, we're just counting 1 bits, rather, sorry. So there's only 1 bit, right? And the parity is odd, and 1's already an odd number, so that missing bit must be a 0. Okay. For an SPI channel with C-pool 1, C-fa 0, when does the data signal change? Boy, this is... So C-pool is 1. So the question is asking about when does the data signal change relative to the clock changing, right? So if C-pool starts at 1 and C-fa is 0, that means that we're going to sample starting on the first clock edge, which will be falling, right? Which means the data must be changing on the rising edge of the clock, right? I get that right? Yeah. Yeah, and the data first changes actually prior to the first edge. So keep in mind that if C-fa is 1, that's a bad example because C-fa. So if C-fa were 0, sorry, was that CFA 0? I'm confusing myself already.
Yeah, I think that was
CFA, yeah, CFA 0, right. So the question was CFA 0. This is CFA 1. So when CFA is 1, remember that the data and the clock change together at the beginning, right? If CFA were 0, the data gets a head start on the clock, which means the first time the data changes would be prior to the first edge. But from that point on, it would be falling edge, right, for that question. Yeah, so first edge is falling. Rising. The data is changing on the rising. Sorry about that. Does that make sense? So let me explain that again. So the first edge is falling because C pull is 1. The first edge of the clock is going to be a falling edge, but the CFA 0 means we're going to read on that first falling edge, right? We're going to read on falling, which means the data changes on rising. Okay? Make sense? Okay, so that was quiz 2. I'll quickly go through quiz 3. If you have any questions, again, just stop me. Okay, what is the result of one device driving a wire to logic 0 and another device driving the same wire to logic 1 using a push-pull driver? So if that happens, you're going to have a low impedance path between power and ground. You got one driver pulling up, the other driver pulling down. That just basically opens up your circuit. The series resistance there is going to be the series resistance through the pull-up transistor combined with the series resistance of the pull-down transistor. So if the on resistance is 1 ohm in both cases, there's going to be a 2 ohm path between power and ground. Right? Now that's not counting these guys that are off because they're like a mega ohm. It has a negligible effect. So in this case, we're just looking at these on resistors, although technically you'll have a little bit of leakage current through the off transistors as well. But the on transistors will give you this low impedance path, 1 ohm here, 1 ohm here for 2 ohms, right? And so if the power supply is 5 volts, then it's going to be 2.5 amps that you'll sink through there, according to Ohm's law. Would you think 2.5 amps would fry these chips?
Yeah, I would tend to think so. The outputs are rated for like 40 milliamps tops, so I would tend to guess probably so.
Yeah. That would probably be enough to fry. Yeah, that's what I would think. If nothing else, they definitely heat up, but it might cause damage.
And at the very least, it would definitely kill that particular GPIO cell. Like maybe the rest of the chip would be okay, but it would definitely kill that particular cell for sure. Yeah, I would tend to think.
Yeah. So the point here is that push-pull driver is real bad for shared buses. You can use them with the tri-state buffers, as I mentioned before. But even then, if there's a mistake made and there's still a possibility that even with tri-state buffers, you got the tri-state buffers are both on with push-pull, and you can fry the chip. So this is the reason why when you're in the maker space, all the SPI peripherals are pretty much just point to point, and it's only the I2C that are multi-master, multi-slave. Okay, so what does a 1-bit signify in the RW slot of an I2C transaction? That is a read. Read. You just have to memorize that, I guess, right? There's no way to reason through that one. That's just what they chose. 1 is a read, 0 is a write. In an I2C channel, what is the value of the SC out wire when there are no transactions in progress? Well, that would be 1 because these are push-pull drivers and the default value for open drain. These are open drain signals. In open drain, the default value is going to be 1. Right? The default value is 1 with UART too, right?
I actually don't know. I think it might be though.
Yeah.
That would make sense.
But that's just a coincidence because UART is push-pull. This is 1 by design because it's the open drain. Okay. Yeah, so this actually looks at the leakage current through the pull-up transistor, or pull-up resistor. What's the result of 2 devices driving a single wire to logic 1 using a push-pull driver? Well, this is kind of a trick question because with, push-pull. If you have 2 push-pull drivers driving the same wire and they're both in agreement, they're both pulling up or pulling down at the same time, then you're okay, right? The problem happens when you've got a conflict, right? But in this case, there's no conflict. So this is push-pull, both pulling up, no problemo. So it'll be 1, right? Yeah. What's the result of one device driving a wire logic 0, another device driving the same wire logic 1 using open drain? Okay, now this is open drain where we now have a conflict, right? But it's a little misleading to say one device driving a wire to logic 1, because if you're on push-pull and you want to set the wire to logic 1, you don't really do anything. You just let it go, right? You allow the pull-up resistor to bring it up to logic 1. So, but and this part's a little confusing. So if I'm on a push-pull wire, if my intent is for that to be logic 1, then I'm just going to not do anything and just say, just claim that I'm driving that to logic 1. If another host on that same wire is setting it to logic 0, then the one whose intent is to set to logic 1 presumably will detect that there's a collision going on, right? But I don't, like I said, I mentioned this in lecture, I don't know exactly what mechanism is used there, but there's some kind of a detection mechanism where I want to set it to 1, so I take my hands off of it, and then I see it go to 0, and then I'm like, oh, well, something's wrong, right? That shouldn't be 0. I want it to be 1. So there is a detection. The driving side is essentially reading it, reading it too to monitor it. Does that make sense? You guys with me? Okay. So in this case, it would go to logic 0. We pull it down. Yeah. Okay. What is the start signal of I²C? Okay, this one is a start signal. Some people call it a start bit. I call it a start signal because it's not really a bit. It's when the clock is high and you drop SDA. And the way I remember that is that whenever the clock is high with I²C, you shouldn't be changing SDA normally, unless you're doing a start or a stop, right? And so clock is high, pull down SDA, that's the start signal. Right. Stop signal is similar, right? So in a stop signal, you bring the clock high, and then you bring SDA high, right? So now this part's weird because this is presuming that they're both low before the start bit, right? So what if they're not? What if SDA is already high? They're not both low. Well, if they're not both low, you got to set the stage. You got to bring them both low, so they got to be both 0. Then clock goes high, then SDA goes high, right? That's your stop bit. So hopefully you guys are comfortable with that after having done lab 2, right? That's what lab 2 was kind of all about. How many times does control of SDA change during a single byte I² read? Okay, read is read. Okay, so read is, there's going to be a change of control for the acknowledgement of the address, right? And then another one for the acknowledgement of the data, right? So 2. There you go. Right. How many times does it change during a write? That would be 3, because when you do a write, you gotta change control for the acknowledgement of the address, then you have to change control back for the master to send the data, then you have to change control again back for the acknowledgement of the data. So 3 times. Right. Right. What is happening during the following I²C transaction? Again, this is obnoxious, but you just have to count bits. There's really no other way to do it. In this case, I think it's a little easier though to read these bits for I²C because you're always looking to when clock is high, right? To read the bits. So you kind of have to label all the bits, and then with I²C, it's like, well, how many bits are there in the transaction? It depends what's going on. It's going to be a multiple of 8 though. So how many is this? I can't even tell. 6, 8, 10. Looks like 16. So right. Or actually 18, right? Remember, each segment is 9 bits each with the acknowledgement. So 18 bits. And so after the first 9 bits, you can kind of draw a line there, and then we have the address, the data, the ACKs, and then that read-write. You got to always remember that read-write bit is the 8th bit in the header in the first 9. Anyway, read-write is 0, so you're writing, and so this is obviously writing, and the address is 4F, writing to 4F. Acknowledgements are both 0, that's good. Data is 3A. And again, you're reading left to right, most significant to least significant there. How can a collision between two I2C hosts be detected? Well, this is what I was describing earlier. If my intent is to put a 1 out there and I'm seeing a 0, then there must be a collision going on. That's basically it. This is a little bit more sophisticated. So drive SDA low. So this is specific to I2C. If I set SDA low, why would I do that? Well, I'm trying to initiate a start signal, right? So I'm leaving clock high. I'm not touching clock. I drive SDA low because I'm trying to initiate. And then if another device is doing that at the same time, it would then probably complete its start bit by driving SCL low, which I could detect, right? I don't know if that's how it's actually done, but that's one way to do it, and it's a reasonable approach. Right? Now what happens if I don't see that and then I drive my clock low to complete my start signal and I just happen to be synced up perfectly with another device? If we're both synced up perfectly, I don't think there's a way to detect it. Like if you just happen to be, I mean, I don't know what the timing granularity is, but if you have two devices that are starting in I2C at exactly the same time, I'm not sure how, I don't think it's detectable. I don't know how that would work. But that's unlikely to happen. On an I2C read, which side drives the clock? It's always the master, right? Yeah. What is the limitation for adding additional devices to a single I2C channel? This one is this is kind of important. This is an important practical issue. How many devices can I have? Well, with I2C, I believe each device is supposed to have its own address, right? And we know we have 7 bits of address. So there's really only 128 possible addresses, right? That's pretty bad. Telling me there's only 128 I2C devices ever made in the world? Unlikely. But there's other issues too, actually. If I were to try to create a bus with, say, 128 different addressable buses, addressable I2C, the leakage current would start to become an issue too, right? Because what you'd end up having, like let's say I had 128 unique devices, they all had 128 unique I2C like MAC addresses. So what would end up happening is you would have 128 pull down transistors there, right, in parallel. Leakage current might be an issue there. So I think leakage current is an issue and number of addresses in it is an issue. Now there is a 10-bit version of I2C, but even then it's 1024. But I've never seen that many devices, right, on I2C. And I think is the ESP32 have multiple I2C channels, right? Buses, right?
Because it has either 2 or 3 hardware I2C channels, and you have as many software ones as well.
Yeah, so there's 2 or 3 hardware I2C interfaces per ESP32. So if you have a bunch of that allows you to partition your I2C peripherals on 3 different buses, right? 3 different channels, so you can split them up. You're not necessarily hanging everything on one. Some devices, I think the Atmel 328P might have only had 1 though, right? Yeah. So some devices just have 1. So, but anyway, the point is there's several reasons why it's not super scalable, right? Oh, collision rate too. I forgot that's also an issue. You might have too much contention on there. Master sees a 1 bit during the acknowledgement slot of a data phase of write transaction. What does that mean? 1 bit means not acknowledge, but this is during the data phase? Just during the data phase, not the address phase. Yeah, it means the right address was received, but the data was not. Okay. How many bit slots comprise a single byte I2C? That would be 18, right? Yeah, 9 and 9. And that's it. Any questions? Okay, so the midterm exam will have questions pretty much like those ones. There was one topic, though, that I didn't get to in the first lecture, and I'm going to cover that real quick. I think it's important. So that was the last bus protocol, which that we cover in this class is JTAG. Okay, so now, by the way, there are other bus protocols we could have covered. One of the really important ones, bless you, is CAN, Control Area Network. That one's kind of like I2C. It's similar, but the level of complexity is higher. It has a much more complex header format in CAN. But if you understand I2C, you can easily understand CAN. CAN's just a more complex version. CAN is the protocol that's used if you have a self-driving car or a self-parking car. It actually is what's controlling the steering wheel and the acceleration. They use CAN for that. My colleague Austin Downey in mechanical engineering just bought a device that he just plugged into the CAN port on his car, and it makes the car drive itself. It's got the cameras on it and stuff. It's like an aftermarket self-driving car thing. It's kind of cool. I thought, wow, that's kind of scary, because that means that anyone that can send CAN messages on your carport and take control of your car, and that's literally, yeah, that's because there's no security in CAN, as far as I know anyway. But anyway, we don't cover that. I thought about adding that, but we never did. JTAG, though, is an important one because JTAG is used to program FPGAs, basically. And it's also used for testing chips. It was originally developed to test chips. The idea is that if you tape a chip out and you put it on your circuit board and it doesn't work, then you're basically done. There's really not much you can do aside from maybe having some probe points on. So when I was in grad school, when we used to tape chips out, we would put holes on the top of the chip. We would put a hole in the oxide layer down to the top metal layer, and we actually had these micro positioners. So you'd have to look through a microscope, stereo microscope, and this had to be done on a vibration isolated table that floated on air. And then you'd have these micro positioners where you turn them and you'd position this little probe, and then you set it down on the chip, and you could directly probe a chip. But that's a real pain, and it requires very expensive infrastructure. I mean, that table, it's one of those, you guys might have seen them. It's those big tables that have all the screw holes in, a grid of screw holes, and then you have to put nitrogen tanks on them so they float. They use pressurized nitrogen, because otherwise you look through a microscope and you don't realize it, but everything is vibrating. Everything in a normal room vibrates. But you don't notice until you look at it through magnification. But anyway, you don't want to have to deal with that. You want to be able to test a chip without having to probe it. So that's why JTAG was designed. So JTAG, the idea with JTAG is that you basically take every register on the chip and you connect them as a shift register. And then the idea is that if you're testing a chip, you don't care about performance so much. You can afford to take the time to read every register on the chip serially, which could take millions and millions of cycles. But that's fine, because I'm just testing, right? We don't really need performance. I just need to be able to capture the state of the chip, the entire state of the chip. And that's what JTAG was designed. But JTAG also has a bus protocol separate from that shifting behavior. It also has a bus protocol that's similar to SPI, kind of. So it's a serial protocol, obviously. It's got TDI and TDO. TDI stands for test data in, and TDO is test data out. And that is equivalent to MOSI and MISO and SPI. It's exactly the same, just different names. Now with JTAG, though, JTAG was designed to support multiple chips connected in the daisy chained, the daisy chain. The daisy chain mode, where you take the different chips and you have the master, which is the testing device, sends test data into the first chip, and then the first chip has test data out that's sent to the test data in of the next chip, and then so forth. And then eventually the last chip in the chain will send its test data out back to the testing host, the master. So that way, not only are you reading all the bits on a chip, but you're reading all the bits across multiple chips in this JTAG chain through this daisy train approach. Does that make sense? Right? So that's what TDI and TDO is. It's the same as using MOSI and MISO in a daisy chain. And then there's a test clock, which is TCK, because JTAG is a synchronous protocol. It has a clock. But the part that's really interesting about JTAG is this signal, TMS, test mode select. This is where things get really kind of, I think is kind of cool. So remember with SPI, of course, we just had slave select. It was just on or off, right? And that was it. And then with, of course, UART and I2C, you had the start and the stop. Test mode select is unique to JTAG. This is something that no other bus protocol I've ever, oh, sorry, this is the, basically how you chain them together. So as I mentioned, test data in comes in, test data out goes out, and then you create this daisy chain. And then, of course, the clock is fanned out. You have one clock that's just distributed to everybody, that's fanned out. And then you have the test mode select, which I was talking about earlier. Test mode select is also fanned out like the clock. So you have one global clock and you have one global test mode select. But the data bits are chained, like in a big shift register, right? So what is test mode select? This is cool. So test mode select allows you to put all of the chips on the JTAG chain in a particular state. And there are, I think, 16 states. Yeah, 16 states. There's 16 states. This is the standardized set of states for JTAG. And so, now remember that we talked about how, you know, first of all, this looks like SPI, but I mentioned how SPI was kind of badly designed if your goal is to have an address and a data, right? Address and data. If you're doing transactions like programmed I/O, where you're doing addressable transactions, SPI is really lousy for that because it's based on doing exchanges, right? Well, JTAG also has the ability to do transactional type behavior where you can set the address and then you can access the corresponding data. So every JTAG device has different registers on it with different addresses. But the way it works is you use the test mode select to put every device in a mode where you can then feed bits in to set the instruction register, which is the address that you want to access. And then when you get done with that, you put it in the mode where you want to put in the data mode, where you're going to shift the data through. So in other words, the idea is that you decide what instruction you want to send out to all the devices in the JTAG train. You take all of those addresses and you put them in a serial, big long serial string of bits. Then you use test mode select to put the devices in the chain in a mode where you're going to shift the address bits through. So this way you can simultaneously set all the addresses for all the JTAG devices with one big shift register operation. When you get done with that, use test mode select to put it into the data mode, and then that turns into a boundary scan mode where you start shifting the data bits corresponding to that address out. That's pretty neat, right? Now the way that works though is in order to change the state, you have to use the test mode select along with the clock to basically walk through a state machine. You guys remember we talked about state machines in 6.11, right? So the test mode select is a single bit. And so if you set the test mode select to 1 and you clock it 5 times, you are guaranteed to end up in this test logic reset state. Why? Because no matter what state you start out, this is the kind of the neat part about this. No matter what state you start out in, you can get to this state with 5 consecutive 1 bits, right? So let's say I'm over here in capture IR. I'll get 1. So from capture IR, I go to exit 1 IR with a 1. Then the second one gets me to update IR. Then the third one gets me to test this state, then this state, and then back to the test mode logic. That makes sense? So if you follow these transitions, you'll get back to test mode, the sanity state, after no more than 1 consecutive cycles of 1 on test mode select. Okay, so that's how you get everything into the sanity state. And then once you're in that state, then you can issue another set of test mode select bits in order to get it into, say, the shift data register. Shift data register, which is where you're shifting data bits out. And the idea there is you stay in that state as long as test mode select is 0, right? So while you're shifting stuff out, you guarantee that you stay in here by keeping test mode select to 0. So in other words, test mode select, you're having to carefully set that even as you're shifting bits in and out in order to stay in one of these. You're either in the shift data register or shift instruction register. These are the 2 states that have the wraparound transition here that allow you to stay in those states for multiple cycles. I think every other state you're going to exit after 1 cycle. Yeah, I think except for these 2 guys. So you can see in test logic reset there's a loop back, and in run test idle there's a loop back. And the only 2 states that have loop backs are, and in pause DR and pause IR, there's these pause states too. But the other states have these, either 0 or 1 gets you out, right? So they're only designed to be in there for one cycle. So in other words, if I asked you, like, what sequence of test mode select bits do I have to put in to get to a specific state from a specific state? So if I'm in test mode reset, let's say I want to get to pause DR. How do I get there? We have to basically figure out what sequence of transitions I have to take to get there. So I got to put in a 0, 1, 0, 0, 1, 0. Right, and that'll get me to pause DR. So I can get to any one of these states just by coming up with a sequence of bits that will reach that state through these transitions. Make sense? So the point is that JTAG has this state machine that's also fed by a serial bit stream, but because it's fanned out to all the devices, you basically set up all the devices on the chain using this, and then when you're ready to start transacting with them, it's just a giant shift register, right, through TDI, TDO. So it would be really cool, I think, to have a bit-banged version of this. But I think that'd be a lot, it'd be a whole lot harder than the I2C bit-bang thing. But you could, in theory, bit-bang this or even design hardware for this, and then you can talk to virtually pretty much every chip has a JTAG interface to it. It's like a back door, essentially, you can get in. And then there's certain registers like, and then there's certain registers that are standardized, certain register addresses. Like there's a specific register address for identifying the chips, right? So that way, whenever you start a JTAG, I don't know if you guys remember this from 3.13 and 6.11, but when you open up your JTAG viewer, it'll automatically detect what chips are on the chain. And I always wondered how it did that. Well, the way it does that is it reads the ID register from each chip in the chain. And so you can actually, you can plug in a bunch of chips on your JTAG chain and then it'll self-identify them by reading their IDs. Assuming, of course, you have a file that maps the IDs to what that ID, there's a table that has to map. It's like a MAC address to, Ethernet card sort of thing. There's got to be a table that maps ID numbers to like vendors and part numbers. Make sense? Okay, so that's JTAG. There's also I2S. This one's, I should mention this too. I2S is also a variant of I2C that's designed for audio, digital audio. This one, though, is a little different. This one has 3 pins. Has this word select pin on it. I think that's for, switching between the left and right audio channels. But the timing is similar to I squared C. Okay, and that's it. Any questions? All right, so final thing I want to talk about today is the next lab. Okay, so this lab is about analog digital conversion. The ESP32 has a 12-bit DC coupled analog to digital converter. DC coupled means that it can read DC signals. Some chips have an AC coupled A to D, which obviously require, that you have, they do analog digital conversion, but only on sinusoidal inputs. The problem, and this is that there's an issue. So the purpose of the ADC in our case, and I think this is fairly common in projects involving this chip, is that you want to use this ADC to read the battery voltage. That's why it's DC coupled, right? I don't think the intent is to do software-defined radio. I think it would fail miserably at that task, right? So software-defined radios, when you use an ADC to directly sample the voltage from an antenna and then use a Fourier transform along with some demodulation logic to actually read radio signals in software, which is cool. But you need a really high-quality ADC for that. And this one's usually AC coupled, I think. This one's designed to kind of get an idea if your battery's about to die. It's kind of the idea. And so that's what we want to use it for. The problem is that in our case, we're assuming the battery is a 14-volt battery. Why? Why are we assuming that? Well, originally, the kind of the motivating project for this board was to control 12-volt motors. So we're assuming that the chip is running at 3.3 volts. The motors are running at 12 volts. And so the battery must be 14 volts.
The battery is 12.6 fully charged. The reason it went up to like 14 is just because that's like the highest voltage the voltage divider can support before it starts feeding more than 3.3 into the pin.
Okay.
The battery would be like 12.6.
But it doesn't go, okay. Does it go? I thought the battery could go up to, okay, 12.6. So
you need a 4-cell to get up to the 14.
Okay, so we were assuming a 3-cell, right? So we're assuming a 3-cell lithium polymer, lithium ion battery. The fully charged voltage is 12.6, you said. But as the battery's capacity goes down, the voltage goes down. And so you can use the voltage as a clue as to what the state of charge is in the battery. So, right, so, but we have an issue because you cannot read a 12-volt signal with a 3.38 analog digital converter. So we put a voltage divider. Do you guys remember voltage dividers from circuits 1? So a voltage divider is a kind of a, I don't know if you call it, like it converts one voltage to another, but it does so wildly inefficiently because it does it just by wasting power, by sinking current unnecessarily through a resistor and heating it up for no purpose whatsoever. That's how the voltage, a very simple circuit though. So the idea with a voltage divider is the ratio between the input and the output voltage is the bottom side of the voltage divider divided by the total resistance here. So in this case, it's 10 divided by 33 plus 10, which is 43. So it's 10 over 43. So the output voltage is 10/43 of the input voltage, right? And so that was selected to drop the voltage that we really want to read, but scale it down to something that's inside the range of the ADC's capability, right? That's the idea. So the problem with this, though, is that your software then has to unconvert it when it prints out the voltage, right? So when your software is going to be responsible for undoing this transformation for the purpose of, measuring or estimating the input voltage, right? Okay, got it? All right, so the problem, though, that we learned, I think we learned the hard way when we started working on this lab, was that the ADC is that doesn't work very ideally. The first thing we noticed is that if you look at the input into the ADC after the voltage divider, so if now we're considering an input voltage from 0 to 3.5 volts or so, right? If you're in that range, one of the things we noticed was that as you ramp up from 0 to 100 millivolts, the ADC says 0 the whole time, the whole range. So dum-dum thinks 100 millivolts is a 0, right? That's because of the inefficiency of the ADC. Now, is that still the case though with the new chip, or was that because that was the old ESP32? Maybe the new one's better, right?
Yeah, S3 has gotten significantly better on both ends. It's still not linear. That's still a big problem, but it's gotten a lot better with just like reading really low to really
Yeah.
high.
So it's not clipping as hard, right? Okay, so it's not clipping as hard, but it's still not. There's still not a linear relationship between what you read and what's actually there. So So the idea is that if I plot the actual voltage versus the red voltage, and of course you could do it the other way around too, but in the old chip, like I said, 100 millivolts was read as 0, and then between 100 millivolts and about 2.7 volts, the voltage that we were reading was lower than it was actually, right? But then once you got above 2.7 volts, the voltage that you read was higher than the actual voltage. So there was this crossover, there was this magic crossover point here, about 2.7. So we had a weird anomaly at 100 millivolts, and we had a weird anomaly at about 2.7 volts. And then, but for most of the range, between 100 millivolts and 2.7 volts, you're reading something that's lower than it really is, right? So we came up with this idea that we could auto-calibrate the ADC. And the way you can do that is you could take advantage of these super expensive power supplies on the benches here. So these guys are, these power supplies do not have this limitation that the ESP32 does. They can very accurately set a voltage based on what you want it to be, right? Because they have a, they have some kind of a feedback controller in there that auto-regulates the voltage. So if you set these guys to be 2.7 volts, they put out exactly 2.7 volts. The problem, though, is that you have to, if you're going to calibrate this, you have to calibrate it through the whole range, right? So how do you, you can't just do 1 or 2 calibration points. You got to calibrate a lot of points for this to work. So then I think it was Alex figured out that these things these power supplies can be controlled by the ESP32. They can be slaved to the ESP32. So in other words, you can write software on the ESP32 that can take control of the power supplies, and that allows the software to have a ground truth reference, because if it sets the power supply, say, to 2.5 volts, it knows that the red voltage is 2.5, well, it's 2.5 times 43/10, right? There's that conversion factor too. But if it sets the power supply to a specific voltage, then it knows what the input voltage is on the ADC, and then it reads the ADC and it looks at the difference. It says, well, there's a difference between what I'm reading and what I know is there because I'm a master of the power supply. So then you can build up this calibration model. You can create an automatic correction mechanism to correct the ADC. Now, you might say, wait a minute, how does that help you between 0 and 100 millivolts? It's just 0. How do you correct 0? Like if you read 0, how do you know it's 0, or how do you know it's 50 millivolts or 100 millivolts? Well, that part you can't do anything about that. Like if it's clipping, you can't do anything about the clipping, but you can correct this nonlinear region sort of in the middle, right? And by the way, the lower end we don't really care much about, because remember, this is designed for battery voltage, and I don't think the 3-cell battery is ever going to go down to below 100 millivolts, right?
No, like a fully discharged one's going to be like 10 point something.
Yeah, so we really only care about the range, upper end of the range anyway. Of course, the upper end is where things get really probably the most wonky in terms of the correction, right? So the idea is basically to auto-calibrate. So there's two parts to this lab. The first part is you're going to use UART to connect to the power supply and talk to it, but we're not going to bit bang the UART. We're going to cheat and just use the built-in hardware UART, right? Which in the Arduino IDE is like one line of code to set it up, and then you just print to that UART, right? You guys with me? You might say print. I thought you'd have binary. No, it's UART. Remember with UART, UART's usually not designed for binary data. It's usually text. So when you talk to the power supply, you're actually using text like English text, which is weird because it's a machine and it doesn't necessarily need to be in English, but it uses English. So you have to like say output 0, you know, like as if it cares that how output is spelled. But anyway, it uses this weird text-based interface, even though it's machine talking to machine, right? And then we're going to go through this algorithm that's going to sweep the power supply output and collect data on the ADC in order to build up a calibration model. And then we're going to put it into a mode where it's just reading. And when you do your demo, we're going to go up and manually change the power supply and ensure that whatever's reading on whatever the ESP32 is printing is a reasonably close approximation of what the ADC is putting out. That will verify that your calibration is working. Does that make sense? So in other words, your program has two phases. It goes through an auto calibration phase, and when it's done, it just sits there and it just monitors the ADC and prints out what it understands to be on the ADC, including its calibration model. Make sense? Okay, so how does the calibration, yeah, let me talk about that first. So for the calibration, we came up with what we think works well. This isn't necessarily the best way to do this. Alex and I went back and forth, came up with a couple different ideas for how to do this. The one we settled on is to use a linear fitted model. So we want to use linear regression. Have you ever heard of linear regression? The linear regression is when you basically find a line that minimizes the error between the points that you're sampling and the line. In other words, you draw a line that minimizes the distance between your line and all the sampled points, right? But that's a linear thing, and I just got done saying that this thing is not linear. So how can you use a linear model for something that's not linear? Well, use a piecewise linear, PWL, which I always confuse with PWM. PWM is pulse width modulation, PWL, piecewise linear. I always screw that up. Piecewise linear, PWL. Piecewise linear is when you can trace a nonlinear curve by dividing it up into segments where each segment is linear, right? So, right, you just kind of build up a curve built from linear segments, right? So in our case, we're going to use 16 linear segments. Now for this to work, this is where things are a little confusing. You have 16 models. You have 16 linear lines. A line is just a slope and an intercept, right? Slope is M, intercept is B. Very simple. But there's 16 different slopes and 16 different intercepts depending on which segment you're in. And the segment you're in is defined by the input that you read. So you read from the ADC, and it will give you a reading that you will then marry up to a segment. You have to use a lookup. You have to figure out what segment it's in. Once you figure that out, then you apply the linear model, right, based on that segment. Okay, so again, you're going to have basically 16 different lines. In this case, I have F1 through F16. There's just one input to each X, and then the output is Y, which is MX plus B, right? So, but they're going to have 16 M's, 16 B's. Those will just be stored in a table. Where do you get those? You have to calculate them. That's what's calculated when you calibrate. So what you're going to do is, as you sweep the scope, you're collecting data points. You're collecting X's and Y's. And as you collect those X's and Y's, you're going to use them to create M's and B's for that segment. And how do you do that? We use a linear regression, and this is a linear regression. This is the formula. There's here for M and B. Now this looks complicated, but it's not really. It's basically just inside these guys you see X and Y, right? X sub I and Y sub I, that's the sample. So X and Y is the sample that you read. What is X? X is the input from the ADC, right? And Y is the ground truth value from that the scope is set for. Because the idea is that what we're doing is correcting the ADC. So when this is done, you're going to read from the ADC, that's your X. You plug it into the model, and it's going to give you Y, or f of X, which is the corrected. It's the corrected form. It's the adjustment. Well, not the adjustment. It's just you're mapping values that you read from the ADC to the ground truth values, right? So Y is your set value on the scope power supply, and X is what you're reading, right? That makes sense? X is the reading from the ADC, Y is the ground truth. So you measure a bunch of those, and you do it through the whole range, of which you've divided into 16 pieces. And for each piece, you calculate M and B this way, right? Make sense? So you might say, why is all the summations in there? Well, because you're adding up all the samples in each segment, right, essentially, right? Or in this case, you're adding up the product of X and Y for each segment, right? That's what's happening here. Here you're adding up X's, here you're adding up Y's, right? And so these are just sums. You're doing these samples and then adding these guys up and getting in the end you have M and B. Okay, so I already talked about that. Okay, so once this is done, this is what it ought to look at like. You're printing out, entering auto calibration mode, taking control of power supply. Your code should know whether it did that successfully or not because of the feedback it gets on the UART. That's why it says success here. Auto calibrating, it goes through a sequence, it prints out the progress in 10% increments, and then it goes into entering monitoring mode, and then it just prints out. Now this is the part that's kind of weird. You've got raw voltage 2.34 volts. How do you get that? Well, this is basically, you read the ADC as is it 8 bits or 16 bits? 16, right?
The ADC is 12.
12. You read a 12-bit value, which is a value between 0 and 4095, right? Then you take that and you divide it by 4096, and that is the ratio that you're multiplying by 3.3 volts to get this, right? So this is a proportion of the 3.3 volts as indicated by the 12-bit value from the ADC. Okay, so that's the raw. Raw is what you read. This is a little confusing because it says, like, what's raw? Raw is just what you read. This is the actual bit value. So 2,904 over 4096 multiplied by 3.3 is 2.34. Then there's the corrected voltage, right, which is what your model gives you. But then you have to correct it again by correcting for the voltage divider. So then you have to take this and divide it by 4310, 43 over 10, 43 tenths. 43 divided by 10, and then that gives you the 11.8. That's what's actually going to be on the power supply. So if you dial the power supply to 11.18 volts, that means that the ADC is reading 2.34, but in reality, the voltage going into the ESP is 2.54 after the voltage divider, right? Assuming the voltage divider has got the resistances there that we think it has, right? Make sense? Okay, and then you just keep printing that out, and that's basically it. So you get to control the power supply. You get to connect the power supply to the board and then use the ADC. Okay, so how do you talk to the power supply? Did I use the whole time up? I did almost, sorry. Okay, power supply. Okay, so as I mentioned, the power supply uses essentially English words that you send it over a ASCII text interface over UART. But that's good because that makes it, fairly easy to code. You don't have to worry about encoding instruction words or anything like that in binary. So, oh, by the way, to set it up, you just say serial to dot begin 9600 serial 8-bit 8N1, 8 data bits, no parity, 1 stop it. And then this is out of date. It's updated in the lab sheet though. The pins are 13 and 14, right?
12 and 13.
12 and 13.
And the ADC pin is now 15 instead of 34 as well.
Yeah, so this is updated in I have the lab sheet. It's just the slides that haven't been updated yet. Okay. So this sets up the serial and then you can just print. The only other thing you have to know about printing is you have to use, every command needs to end with \r/n because it's using the old carriage return new line convention that Microsoft has cursed us with for the past 57 years. As opposed to just the Linux style, new line, \n. You got to use \r/n. Right, and then so the command set is here. If you type inst:\n cell x, you can select a channel. These guys have 3 channels. I think, yeah, the first 2 channels can go up to 30 volts. The third channel goes only to 5 volts, but for the most part, you obviously want to use channel 1 or 2 because we want to go beyond 5 volts. This sets the voltage of whatever channel is selected. This sets the current limit. This command enables it. You can have it beep. You can even display text. This is kind of a fun little novelty. But this command, disp:\text, allows you to print a message on the power supply, on the little LED display. So yeah, so it's basically, it's just, the commands are all listed in the lab sheet. Okay, so one other thing I haven't mentioned yet is the calibration. What are we calibrating? What is the increment? What's the increment for the calibration? Is it 100 millivolts or what do we do?
50 millivolts.
Okay, so yeah, so the problem is that you have to go from 0 to 14?
You can do a little over 14, maybe 14.2.
14.2. So the range is 0 to 14.2. The problem is, what is the increment? I think the first time we did this, we were using something really low, and it took forever to get all the way through that range. I think last year we relaxed it to 50 millivolts, whatever it says in the lab sheet. But the increment is how much you're going to increase the voltage with each step. And you might say, well, come on, man. It should go pretty fast, right? I mean, it's the 200 megahertz chip. I mean, it's probably, what, millisecond to get through that range? Well, no, because remember, you're dealing with the UART and the communication. It's the rate at which you go through this is like 1 voltage every, I don't know, 100 milliseconds or something, right? It's kind of slow.
And you have to give the power supply time to stabilize after you change the full peak voltage, because if you don't, it'll give you a voltage that isn't correct. And yeah.
Do we give them that in the? Do we have a number for that? I don't remember. Is that just an arbitrary way?
It's kind of arbitrary. Just wait a little while to
Okay.
give it time to stabilize.
I think the lab sheet, hopefully the lab sheet says that. But what Alex is saying is you don't necessarily want to go as fast as you can because the power supply, even after you wait to send the command to set the voltage, it doesn't instantly change the voltage. But you can change the voltage while it's on, right? While it's enabled, right?
While the output's enabled?
Yeah.
Oh, yeah.
Yeah.
Absolutely.
Yeah, so remember, I don't know if you guys use power supplies, I think, in electrical in 201, but power supplies normally are designed for you to set the output voltage and current before you enable them, right? And typically, usually you're not changing the voltage while they're enabled. That's weird, right? But we are in this lab. But you don't normally do that. Normally, you set them up ahead of time. The only thing that irritates me about these power supplies is that when they're not enabled, it doesn't tell you what the voltage is. It says 0. So like, let's say I want to set them up to say 3 volts, but I don't want to turn it on yet. Well, you're not going to see 3 volts. It just shows 0, right? I don't know why it doesn't tell you what the set point is when they're not enabled, when it's not actually energizing the outputs. I don't know why they do that. But in this lab, you're just going to set them to 0 and then enable it and then walk up while it's enabled, right? Yeah, you can do that, right? You can change it while it's enabled.
Yeah.
Yeah, it's not normally something you do with a bench power supply, but we're going to do it because we're going to sweep through this calibration range.
That actually brings up an important point. Don't go over 14 point something volts. Don't set it higher than that because you can fry the board, because that'll take a pin over 3.3 volts. So cap it there. Don't go any higher.
Yeah, and one other thing too, when you plug the power supply, so do we have any of the I don't know if we have them.
Are you looking for serial cables?
No, alligator clip things.
Anybody have like a set of red and black?
I think I put them all in the boxes over Christmas. Yeah, we have the cables in the box, but basically we have cables that are one end are a banana clip you plug in the power supply. The other end is an alligator clip that you're going to just clip on. But make sure you clip it on the one that says VBAT. VBAT is the high voltage one. The other one, of course, is just 5 volts. It says 5 volts. So you've got it labeled 5 volts and you got labeled VBAT. Use VBAT and ground. We're not connecting anything to 5 volts here because the 5 volts is supplied by the USB connection, right, to the computer. So you don't need to connect anything to 5. The VBAT is designed to be the 12 volt battery, right? If you wanted to run this without a USB connection, you can by connecting a power supply to the 5 volts. If this were being used in our standalone motor-based thing, then we would be supplying the 5 volts for the ESP32 and the 12 volts for the motors. We don't regulate 12 down to 5, right?
If we were doing the actual project, though, I'd probably put a switching regulator on
yeah.
though, to regulate it down to 5 volts.
So we don't have, like, you cannot power the ESP32 off the VBAT input.
Not right.
The VBAT input is used for the ADC. It's used for the motor connectors. These are motor connectors. And it's used for the sound, right, the speaker.
Yeah, the speaker. Yeah.
Speaker. So we have a speaker circuit, a motor circuit, and the ADC circuit are the VBAT. Everything else is powered off of 5 volts or, the USB 5 volts, right? So yeah, just be careful where you plug the power supply and don't go over 12.6 or 14 or whatever. 14.
I think.
Yeah, don't crank it. Remember, the power supplies go up to 30, so you can easily blow these things, okay? Any questions? Okay, now normally we only give, I think, a week and a half or so for this project, but I extended it because of the midterm. Normally, last year we had it due on March 6th. Well, actually, it was March 7th last year because it was one day off, but March 7th, but I made it March 13th for the due date so you guys can, study for the midterm. Okay? But the project is not, it shouldn't take you that long. It's because remember that this part is just, the UART part is like just a couple lines of code. The ADC part is a little bit more complex because you got to calculate those M and X's, but even that's just a few lines of code. It's not too bad. Any questions? Yes?
You extended it a week. It is intentional then that the 13th is that Friday over spring break?
Oh, that's right. That is spring break, isn't it? Yeah. Then I'll have to, we're going to have to push it past spring break, right? Yeah, so I'll extend it one more week. Yeah, so it'll actually be the 20th. Yeah, I feel bad though, but yeah. Well, last year we did, the reason I avoided spring break last year is because we did an online midterm then, but we're going to do in-class midterm, so it messes things up a bit. So we'll extend it. Okay. All right, that's all we got. I'll be right with you.